All right, welcome back, everyone. Okay, all right. So we were at with principal component analysis before. So the idea then, right? It is a way to reduce the dimensionality of your data set in a way that fairly precisely captures the amount of explained variance within your data itself. Okay, and so it applies a transformation to your data set that actually sort of ranks your columns in terms of how much information they contain. All right, so what we had before, if we kind of go through here, I may have forgotten it already. Okay, my apologies. Okay, the idea here, right? So you call PCA the fit transform method, right? So you have this variable right over here, and then when you're done, right, you have this thing called the explained variance ratio, which basically means, right, first column, right, contains this level of variance, second column is this one, third is this one, and so on and so forth. It's important to understand, right, the columns that come out of PCA are not your original data set, okay? It's actually a projection of your data set into in a lower dimensional subspace. Again, that distills the level of variance into as few columns as possible. So it's like the column here, right, that contains this level of variance is not just a single column in your data set, right? It is essentially a blend of different information in your data set into something else, which is an important thing. So sort of the original column labels that you had before are not going to apply to these things right over here, okay? That's an important idea to go ahead and understand. Right, so the idea then, right, if you say PCA, right, with a number of components that explains 95% of the variance, okay, the corresponding result on your model really will correspond almost exactly to 95% of the original R squared value that you had, okay, almost exactly, right? And then because it uses the transformer API, you can just as easily go ahead and then stick this into a pipeline like we did right over here. Right, so if we're doing linear models, we have the scalar, we have PCA, and then we have linear regression right over here. And so then the idea is, right, you can fit like this on X, and then the same way, right? Predict, just like we did before. Okay, and then these, right, would be our new predictions like that right over here. Okay, so the idea then, right, if you seem to have a data set that is unusually noisy, you want to have a way to give yourself maybe more reliable and reproducible results. PCA is essentially a way to smooth your data, okay, into a sort of different representation of your data set, which is more compressed, and then contains a larger signal-to-noise ratio that is going to give you more reproducible results, okay? It tends to go hand in hand with linear regression quite a bit. And so very, very frequently, the combination of a PCA and then something like Ridge or Lasso, pretty frequent 1-2 punch for various things, okay? So it is a useful toolkit. I would say definitely widely used. You can do it on almost any sort of data set. And so I would say probably one of the more popular ML techniques, not very well publicized. Because in a lot of ways what it does is not very sexy, right? It just kind of like reduces your data set to something a bit more useful. But definitely very, very, very widely used. And then easy enough to go ahead and implement. And then again, if you go over here, I'll type this in, SciKit learn. And then take a look at the decomposition library. So vanilla PCA is the one that's used most frequently. Okay, but there are about 10 different flavors of PCA that you could potentially use, right? So PCA is the most common one. Okay, another one I'm going to take a look at here, it's worth pointing out here, it's also called truncated SVD, okay? You can essentially think of this as PCA for sparse matrices, okay? The idea behind this is that sometimes you might have data sets which might have something like 100,000 columns and then 50,000 rows. Those are just naturally going to be very, very difficult to work with. And so truncated SVD is a form of principal component analysis which is designed specifically for those sorts of scenarios, okay? So most of the time, regular PCA will be pretty good. But in the special circumstance, right, when your data set is much wider than it is tall, then truncated SVD would sort of be the analogous technique to go ahead and use in that situation. Again, the API is basically the same. You know, there's fit, transform, and things like that. So like kind of the implementation wouldn't be any different, but they have slightly different use cases. Okay? So in any event, hopefully this helped, and I look forward to, and sort of hearing how you